That is ostensibly the opposite of breakdown, as the chain length gets longer rather than shorter. Perplexing. But Krebs had a clue, which others may have overlooked as irrelevant. The C6-carboxylic acid citric acid, which is responsible for the tang of citrus fruit, had recently been shown to break down in several steps to give the C4-succinate. That gave quite a long series of apparently interconnected steps, which ran from the C6 citrate via a C5 intermediate, called alpha-ketoglutarate, to the 4 C4 carboxylic acids. It had not escaped Krebs's notice that these steps released 2 CO2 molecules, as the carboxylic acids were clipped down from 6 to 4 carbon atoms in length. Presumably, these steps, in which CO2 was pulled out, needed oxygen to go ahead. Krebs also found that adding citrate to his pigeon breast slices, he'd modified St. György's method, sped up respiration in a similar way to succinate. Citrate was definitely involved in respiration. In a coup de grace, Krebs showed that if he added citrate to the tissue slices along with an inhibitor of respiration, then the succinate now accumulated. That could only mean that the pathway from citrate to succinate and onwards was indeed a normal part of respiration. Blocking respiration led to the accumulation of these intermediates. In short, Krebs now had a succession of intermediates which somehow went from pyruvate, C3, to citrate, C6, then alpha-ketoglutarate, C5, and finally succinate, C4. Adding any of these intermediates had a catalytic effect, speeding up the overall rate of respiration. It all added up to pretty much the scientific equivalent of a cryptic crossword puzzle.